think we've overcome these technical difficulties. Yes. Okay. Homework 7B. Okay, let's have a look at this assignment. There were a bunch of questions about it. All right, and let's just get some graph paper here. So the first one is contains, so we need to figure out when one rectangle contains another. So let's first draw the happy day picture where it's true that one contains another. So here the black one contains the red one. And now you'll notice in the class that I gave you a couple of convenience methods. It's the tester. I gave you not so much methods, but convenience fields, really. I gave you these max x and max y. So you still construct the rectangle in the way that you've always done it with x, y, width, and height. So I didn't want to change that. I figured that's what you're used to. But then in the constructor, I compute the maximum x and the maximum y value. That's just the minimum x plus the width, the minimum y plus the height, because it turns out they're more useful than the width and height for these kinds of problems. So let's label these here. So here we have x, max x. I guess I should put this x over here. And here we have y. Down here is max y. X, wrong one. Y, max x, and max y. So here's our little picture. So when you now compare the black x value and the red x value, and so the black x value is the x of the, let's say, the implicit parameter, and the red one is the one of the explicit parameter. That would be other.x. What can we see? So what's the relationship between the x's?
X of the smaller rectangle should be greater than or equal to the x of the
Right. So we have so the red one is other. Less than or less or equal? Let's see if the problem talked about that. Is entirely contained in the first. Oh, the tester had something to say about that?
Yeah, whenever I put less than it, see the first line system dot print line r dot contains r.
Okay. Oh, excellent, excellent. Yes. So r contains r is supposed to be true. So that means that if the equal should also be permissible. So it's less than or equal. So apparently containment just means it doesn't fall outside, just like set theoretic containment. That's fine. So that's one of the conditions. Now let's look at what happens with the max x's. So the max x of the black, now compared with the max x of other, you see it goes the other way around. It should be greater or equal other.maxx. I saw some nervousness about that on Piazza where people said, why does it go the other way around? And I think the only way to know why it goes the other way around is to draw the picture. Yes?
Do you prefer to say this dot x, or is there a decision?
It's up to you. It's actually a little clearer to write this dot x, but right now certainly right now I can do anything, right? It's just a piece of paper here. So by all means, write this dot if you find it clearer. It's something that every once in a while I would like to require students to write this dot for everything, because it makes it totally obvious that what refers to the implicit parameter. And every time I try that, there's some reviewers who say, this looks so strange. And so then I give up. But I know a few professors who do insist on that actually in the CS1 course, and later students can drop it, and it's not a bad idea. So by all means, feel free to write this dot if you find it clearer, and I will actually follow your lead and use that in this solution that I'll code up in a few minutes. Other questions so far? So now the relationship with the y's is the same, and I'm not going to write that down. So let's just see what we can do in terms of coding. Let's run BlueJ. This is homework 7b. Huh? Ah. Rectangle. Okay, I'm going to grab the tester too. Okay, now I have three methods. Here they are. Line things up, edit. Okay. Okay, so we have what? 36 test cases. I'm not passing very many of them yet. So, contains. Notice, by the way, that the two methods called contains, one of them has these two integers, and one of them has this rectangle. So if I just follow the logic that I just had, then I'll say return what? This dot x is at most, no, it's less equal other dot x, and this dot y is less equal other dot y, and this dot max x is greater or equal. Okay, let me actually do it this way. And other dot max x less equal other dot, no, this dot max x and other dot max y less equal this dot max y.
So leave the x and the y on the max and then below.
Oh, that's nasty. Okay. Thank you. Compile. Let me clean up. Control Shift. Okay, let's see how we're going to be doing on this. False, 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 false. Oh, question. True, 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 false, 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 false. Okay, that seems good. How many test cases are actually this method? No, more than that. 8, 9, 10, 11, 12. All right, so I should double check that the first 12 of them match. True, true, false, 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 false. And they do, so I am done. All right, so let's now have a quick look at this code here to see what we've achieved. So notice that we have a statement that is of the required form. It's return, and then it's just one long condition that says that the first one should be less than and, the second should be less than and. So this is a Boolean expression that's either true or false, and we're just returning the value of that Boolean expression. And so it's not that different from the code that's up here, where we were just testing whether a single point lies in the rectangle. Yes?
We're able to access the max x and the max y of other because this is running the main program.
Okay, so that's a very good observation. And so what he notices is that over here, I'm referencing other.x. Did anyone ask this on Piazza?
I just created a return function.
Oh, you just added some extra methods. I see. I see. So it turns out that the way it works in Java is that these instance fields here that are marked as private, they can be accessed by every method in the rectangle class, and it doesn't matter which rectangle object. So the privacy extends to methods in the rectangle class, and they can do it on their own object, on this, as well as any other object. So if you've created additional accessor methods, that would be another way of dealing with it, of course, but it was not necessary, and I didn't really expect that. So the shorter way is of doing it this way. Now, there is a shorter way. So when we look at the picture again, let me get some very visible color. How about purple? What's the shorter way? So notice those 2 points, x, y, and max x, max y. The red rectangle lies inside the black rectangle if those 2 points are inside the black rectangle. I have a method to test that. So So that's shorter and also easier to understand.
Contains to less than or equal.
Yes, it does. It's a very good point, and I just checked that myself a minute ago. So he asked whether the contains does less than or equal, because we were pondering whether it should be less than or equal. So it does the right thing. And that is not by accident, because when I designed it, that's what I did. So I didn't expect that anyone necessarily gets to that insight, but I want to point it out that that is a good solution, and it shows the power of these helper methods. Notice, by the way, that I could write here this dot. And some of you may like that because it makes very clear what is the object on which we call the contains method. You don't have to do it. Maybe it's perfectly reasonable for you to think of it the other way, but have a look at both ways and see which of the two you like better. All right, so now let's go back to the problem here. And so intersects means that the two rectangles have at least one point in common, but neither contains the other. And is disjoint from means that they have no point in common. So assume for a minute that I could already do is disjoint from. Then it tells me here what intersect is. It says it's not disjoint because this condition here is the opposite of this condition. So it's not disjoint, and neither contains the other. So that's intersects. I'll write it right in here instead of a scratch paper. Not disjoint, and neither contains the other. Right? Now, you have a method to check whether it's disjoint. You have a method whether this one contains the other, and neither means you also have to check whether other contains this. So you can do this one by just calling some of the other methods and combining the results without having to fuss with any less than or equal signs. So I think that's a useful tip. But it does mean we still have to worry about is disjoint from. So let's look at is disjoint from. And once again, we need to write we need to draw a picture. So we have a rectangle. And now let's look at the various possibilities. How another rectangle could be disjoint from it. Now let's see if we can do again the trick with the corner points. Can we say the rectangles are disjoint if the black one doesn't contain the corner points? Say again? Well, but I mean, we have no method for touching. So we have a method to check whether the black rectangle contains a point, or contains another rectangle for that matter. And so my question is, previously I was able to solve this one, whether it's inside, by saying if both of these corner points are inside. Now, which was kind of a nice trick. And so I'm trying to resurrect that trick. Can I now say, if both corner points fall outside? I have to do all four. And that is actually a very good observation, because watch this one. Right. So here, neither of those 2 points are inside the black rectangle, but this stuff here overlaps. Excuse me. So, and also the other situation would be this one, where even all 4 points don't really help me. Right. So it looks like we're going to have to try something else. So let's look at I just want to have this one here. I don't want this one. Let's look at a simple situation here. So we need an idea to see how can we conclude that the tan rectangle is disjoint from the black one. And so if we again do our x, max x, I think it's simpler than that. Yeah, so what seems up, when you look at this here, if the condition that seems useful is max x is less than other dot x. So let's ponder that. What that means is that there's no possibility of any intersection, because one of them lives like in this half of the world, and the tan one lives outside that half of the world. So they can't possibly intersect. So that seems like a good condition. How could we capture that it's on the left? So by the same kind of idea, that you could say they are divided in this way here, and so that would be other dot max x is less than x. That means it lifts all the way to the left. And then, of course, you have the, on the top and on the bottom. Well, what if it's up here? Well, then it's still all the way to the right and all the way to the top. That's even better. And if it's like somewhere up here, then it's still on the top, but not all the way to the left. But it is all the way on top. And so if you follow this idea through, then you will come up with a valid condition. Another question then is do you have to or the conditions, or do you have to and the conditions? You have to or them if it's all the way to the left or all the way to the right, because it can't possibly both. Right? So that already gives it away. So that's how you would have to do this one. And again, I can't overemphasize that you have to draw the picture. I've tried to do this on the train, and after a couple of minutes I drew the picture. It was just not worth thinking about it. And once you draw the picture and you try a few things, then it becomes reasonably clear. But you also have to give yourself the time to try a few things. I did try the thing with the corner points first, and then I got nowhere with it, just like what I just showed you. And so you just have to be able to try, give up, and then try something else. And that's often surprising to people, because people always think there's a cookbook. There's like one way of doing this, and there is no cookbook. It's a different twist every time, and you just have to generate a bunch of ideas and play with them, and then kind of see which ones are likely to come to success. And ultimately, that's what people find hard as we enter this section of the course. It's not so much the ifs and the while and the for statements. I mean, those are fairly straightforward. but what people find really hard is to generate these ideas to how to solve a problem. And it's the logic of it more than the actual reducing it to programming. I'm hoping that now that I've worked through the logic, that you're going to be able to quickly write the code for it and fix the usual bugs that we all make when we do that part. But the hard part really is, how do you generate a plan? And that's also why in the labs now there's a whole sequence of labs that tries to get you to generate a bunch of ideas and to work through those ideas, to run them through in pseudocode without going to actual code. So what students invariably do at this point is they try to rush to code too quickly. And then they try to tinker with their code in the hope that they can beat it into submission. And we're right now at the time we can no longer do that. That worked fine for the first few weeks of the course, where there was so little Java that you knew that there wasn't really much to the solution space. I think the last homework assignment, the one with the triangles, showed the limits of that strategy. And so now we're definitely getting beyond that, and so you have to really think through this first. But let's face it, if there was a recipe, if there was like a computer program that could just read this thing and write the code for you, then there would be no point for us to be here and learn this, because then why would someone hire you if they could just run the program? All right. The parent-grandparent thing. Let's see whether there's some concrete questions. What constitutes a sibling? Okay, let's just go through the whole thing. So this one is a really interesting question because of the null, which we haven't really worked with so far. So let's look at the class here. Oh. I just close BlueJ. So there are two ways of constructing a person. Maybe I know the parents, maybe I don't. And notice that this is an oddly self-referential class. So a person has a person as a father and a person as a mother. So if I were to draw a diagram of what this actually looks like in memory, it would look like this. And this one even could point to other objects, right? Or not, in which case there would be a null in here. Eventually, it should point to null because it has to be a finite data structure. So now someone asked, how can we tell whether two people are siblings? And it said in the description that siblings have to have the same father and the same mother. So these two would be siblings. And that's actually easy enough to write in code. I said they have to have the same father and the same mother. To find out whether this is the same father, I compare father, or I'll just say this dot father, and I have other dot father. How do I find out whether they're the same? Yeah, I can just use equal, equal, and that shows whether they're the same object in memory. And then you do the same thing with the mother, and then you return. And I'll leave that to you to fill in. And that's how you would do is sibling. Let's look at is grandfather. I'll just implement his grandfather right now. I'll leave it to you to. So one brute force way of doing it would be to say this, right? The problem with that is that you have to, at this point, make a null check, because it's possible that other dot father is a null reference, and then if you call dot father again on null, you get a null pointer exception and your program dies. And for that reason, when you look at the tester for this one here, you see where I'm catching these null pointer exceptions. You don't yet know what it means to catch an exception. That's syntax that you're only going to see in the next semester. But I put it in here so that the tester doesn't die if you make a mistake. I learned that the hard way, that I would have some poor student who the fourth test killed the program because the student made a mistake, and then all the other things weren't tested at all, and the student lost like 20 points or something. And so now I've learned that when there's something sensitive going on, that I'll make it so that I execute the test, and if an exception happens, then I'll print the null pointer exception, and then the test will fail, right? Because then it'll say null pointer exception expected false, and but it'll keep on running. So that's the reason for those. So you need to be a bit careful here with these things, that you worry about the possibility of these things being null. Otherwise, you will miss some of those test cases. This will undoubtedly happen to some of you. You will run the tester, and it'll complain about some null pointer exception, and then that's the reason why. Other questions about the person thing? So I guess I should point out here, this is not complete, right? That it could also be that the grandfather, that it's on the mother's side. And so you could try to use this parent. Maybe that can help you somehow in making the conditions simpler. And definitely don't forget the mother. If you do it exactly right, that is actually true. That happened to me too. When I looked at it, I made the same observation, and just by sheer dumb luck, I managed to have written all of the tests in such a way that I never had to check for null.
Yeah, it's like
But
I left where null is always the other
yeah.
alternative.
But there are 10 other ways of writing it where you would do something like this here, and where there would be a null pointer exception. So I felt I did have to explain that you need to handle it. And I couldn't say, don't worry about nulls, because at some point there will be nulls. There's no way of writing this, this set of parents and grandparents without eventually coming to a null. Okay, any other questions about the parents? All right, it's not an easy assignment, so make sure to get going with it soon. And I think it's one of these things that that is really baffling right until the moment when you figure it out. And at that point, you look at it and say, well, that was actually very simple. But in my experience, it can take students quite a bit of time to get to that point. So don't wait until Sunday afternoon. Inspiration doesn't strike like that. All right, on to the lecture. Okay, for loops. So there are loops that have this particular structure where you have a variable that gets initialized, that you then test against some bound, and then you increment or decrement it, or maybe add 2 to it, and then you do something inside that loop. And the exact sequence is you first initialize the variable, then you test, then you enter the loop and do its thing, then you do the increment, then you do the test again, then you do what's inside here, and so on. So the for is a convenient shortcut for this kind of loop where the various control conditions, the initialization, the test, and the update are all collected at one spot, so it's easy for you to see that you're using the same variable, and where it's neatly separated from the body of the loop that does the actual work. And so you would always want to use a for loop whenever you have a variable that runs from a particular starting value until some condition is fulfilled, and then that same variable is updated. That's what it's for. So it happens a lot. You're going to find that probably half of the loops that you write in your life have this form. That's why they get special treatment. So the one thing that's a little bit noticeable when you look at the flow chart here is that you have the initialization here, and then the test. And then you go inside the loop, and the third part, the update, happens at the end. Let me make this a little smaller to make this point clearer. So this here is the body of the loop. This is the initialization. This is the test. This is the update. And so they happen in this order. But when you write the loop, you write for, init, test, update. You write them in a different order than in which they're executed, because the update only happens after the body. And so that sometimes people, when they see it for the first time, find that confusing. The reason that one writes them in this order is you want these three things together so you can quickly look at them and see that they are really related. You could, in theory, put absolutely anything into the initialization, test, and update. The Java compiler doesn't actually know what's going on, but that would be considered a nasty thing to do. So here we have an example. I want to know what is my balance after some number of years. And so here I wonder for I goes from 1 up to a number of years, so the condition is I less equal number of years than I plus plus. I'd simply compute the interest added to the balance. So I'm just running this thing number of years times. So really what I want to be able to say is sorry about that. There we go. I want to say run this number of years times so that's how I would write it in pseudocode. I would indent the stuff that I want to run number of years times, and to translate this pseudocode into Java code, that's what you see on the left. And that brings me to a point. A couple of years ago, I watched students doing the lab that you just went through, the Lab 8. and where you have to write some pseudocode, where you have to discover an algorithm to do something. And I realized that students had a great deal of trouble with that process. And so I asked the first group, okay, what's your strategy? And this was the one. Let me pull up the lab so that it's less abstract. And you'll see in a minute, there's a pointer. What I'm trying to say. Labs. So the lab was to count how many syllables a word has. Did everyone do this yet? Yeah, so I'm not giving away an answer and make the lab instructor mad. All right. So, so we have a word like beauty. And so I said, what's your strategy? And what I expected students to say was, okay, we'll look at the first character. We'll look at the second, the third, the fourth, the fifth, the sixth character. We'll look at all of the characters. And if we find that we have a character that's a vowel, and the next character is also a vowel, then we'll do something. So that was what I kind of expected that students would do. They would explain to me, just in plain English, how they would look at characters, make some decision how what happened if the next character was also a vowel, the previous character was not a vowel, or whatever. And I had like 8 groups of students. 7 out of those 8 groups of students told me, I think we need to use a for loop. And so my heart really sank, and I realized that I needed to have more labs that have to do with problem solving and not just programming. Because at this point of the game, it is completely immaterial whether you use a for loop or a while loop or any other mechanism. That's just implementation. It's like if someone asks me, how do I get to your house in San Francisco? And I say, I think you need to use the gas pedal. So, so when you think about these things at a higher level, it is well worth saying, do n times, or for each letter, or what are we going to have in the next assignment? Yeah, we'll have a bunch of them where it says for each letter, for each number, for each input, something like that, that just says what is the purpose of the iteration, what it is, or like we had something last time where we did something for each digit. If you write it like that in the pseudocode, then you can later figure out how am I actually going to get each digit, how am I actually going to get each letter. That's just implementation. That's the gas pedal. But the higher insight is you want to traverse something and look at whatever it is that you want to look at. So in this particular example here, the pseudocode would say for each letter, if it's a vowel, and it's okay in pseudocode to say if it's a vowel. Of course, later when you write it up in code, you have to say if is vowel of letter. But in pseudocode, it doesn't matter. So if it's a vowel, okay, then what do we do? Counter plus plus. By the way, it's okay in pseudocode to write counter plus plus. It doesn't have to be plain English. I like to write plus plus in pseudocode because it's faster to write increment counter. Right? So pseudocode is there for our convenience. It can be code, it can be not code, whatever is fastest for us to record our intention. So if you do it like this, that doesn't quite work because then all you do is count the vowels. So how do you manage to count the syllables?
Check the next letter is a consonant.
All right. So you say if it's a vowel and the next one is a consonant, then you do counter plus plus, okay? And this is beautiful pseudocode, right? Notice that at this point it's kind of far away from Java. What is the next one? How do we even get at the next one? But that's something that is solvable, because to get at the ith letter, as you know when you looked at the previous part of the lab, you call what a substring of I plus 1. And then it's plausible that if you can get at the ith letter, you can also get at the next one. So that's a minor problem that we're not worrying about when we first come up with strategy. So, and the other thing that's nice about thinking at this level is that you can already see that you did it wrong. Where does this pseudocode fail? So let's look at the very last one here. So I say, okay, that's the letter Y. It's a vowel, yes. And the next one is a consonant. But there is no next one. So you have to say and. Either next one is a consonant, or there is no next, meaning this is the last one. And then you do counter plus plus. So even at the level of pseudocode, you can already find these kinds of logical errors. And that's why what the lab made you do is walk through the pseudocode without ever writing it up in Java. And it is a totally useful skill. All right. Back to the lecture. I can still find it. Okay, do I want to do this? Sure. All right, so this question tries to get at whether for loops and while loops are really equivalent. That's option 1. Whether for loops are a special case of whiles, whether while loops are a special case of for, or whether they're just kind of different. They overlap, but they're different. So this shouldn't take you too long. All right, let's see. Oh, that's interesting. Wow. All right. Let's see, if every for loop can be rewritten as a while loop, and the answer to that is got to be yes, because if you have like for I equals 0, I less than n, I plus plus stuff, you can always write it like this: I equals 0 while I less than n stuff and I plus plus. Right, so that transformation is always okay. So every for loop can be rewritten as a while loop. And why do we have for loops at all? Because they look neater than the equivalent while loop. So now let's say I have the opposite. I have a while loop that says while some condition to stuff. Here's the equivalent for loop. So I simply leave the initialization and the update blank, and it's the same thing. So the while construct is not strictly necessary. You could write all the while loops as for loops, but they would look ugly, right? That loop looks weird. In fact, you could even put, if the stuff is a one-liner, which it sometimes is, you could put it even in here. And then you have to put a solitary semicolon in the body. And I've seen people who write loops like that, and they look totally bizarre. And so you shouldn't do it. So the idea is to use, as a practical programmer, to use the while loop when you have like a general iteration that doesn't fit that particular for pattern, and to use the for loop when it does fit that pattern. And that way you give a clue to the reader what kind of loop it is. So the majority thought, what was it, option 3? All right. So it's not a big deal. I just wanted to point out that for and while can be expressed in one in terms of the other. Yes, and I do definitely want to do this one.
I think the reason why I got blue is because it looks like really
But there's a big difference, as every student knows, between can and should. All right. So this is also a straightforward question, I hope. So I put this up because it's such a common error. So people look at the 10 here. Yeah? Internet's closed again? Okay, well, I'll leave the poll open for a bit. The premiere? Okay, well, we'll leave it on for a couple of minutes. So, so the 10 makes it look like, it's going to be 10 times. But notice that we're starting at 0 here. And so this kind of, so let's see what people are doing this time. I'll just give the answer away. Yeah, and so the vast majority of people figure out it is 11 times. Because, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that's 11 numbers here. As you can plainly see, these are already 10 numbers, so there's an 11th number. This kind of error is very common, and when people talk about it, they might say, you made a fence post error. And so the term fence post error comes if you have a fence with, say, 4 segments, then it has 5 posts. So it's not directly related, I guess, but so this off by 1, right? That you have 1 extra one is called a fence post error. All right. So it's worth noting that it happens when these fence post errors happen whenever you have what's called symmetric bounds. So when you have an equal here and a less equal here. So which really means you have an interval where on both sides you include the bound. And then you get one more than you might naively expect. So for example, in this case here, where I go from 10 to 20 inclusive, then that's 11 numbers. 10 to 19 is 10 numbers, and then the 20 is the 11th number. And so in general, if you have a loop that goes from A to B, and you include the bounds here, then it's included B minus A plus 1 times. So when you start with A equals 1, where you say for I goes from 1 to n, then this 1 here cancels nicely against this 1 here, minus 1 plus 1 here. And then this loop really does get executed n times. If, on the other hand, you start with something other than 1, like 0 or 10, then you just have to keep that extra count of 1 in mind. Sometimes that's what you want. Sometimes it's not what you want. The other style of bounds, where you have a equal on one side and a less than on the other side, is called asymmetric bound. So here the interval is really 10 less equal I less than 20. So you notice the less equal on the left and the less than on the right. And those ones here get executed B minus A times if you have an A on the left and a B on the right. So you don't have that plus 1. So there's some people who say you should always write your loops asymmetric. And I'm not sure that I would go that far, because if you have a loop that looks like this, that looks like a beautiful loop. It gets executed n times, and many times you do want to start with 1, so why not? But some people give that advice. And it actually, as a practical matter, happens very, very often in Java, because in Java, position values start at 0. The positions of a string get counted at 0. Right, so if you remember the string hello, the positions are 0, 1, 2, 3, 4. And so then you start with 0, and then you want to go to less than the length of the string. And that gets executed how many times? The length of the string. And that's how many characters you will want to visit. So this is a very common loop. And when you see this, you just need to remember, how many times do I iterate? I iterate this many times from 0, 1 to up to string.length minus 1. So traversing strings is traversing string is something we're going to do a lot in this course, simply because they they're there. It's easy to come up with assignments for them. And once in a while, you come up with something that's actually kind of interesting. So to get through all of the positions of a string, it is this loop that you should simply commit to memory. Your fingers should be able to type this thing on autopilot because it happens so often. What if you want to traverse them backwards? You can do that, and notice how it's done here. Now it's not quite so pretty. I have to start at the string length -1. That's the last valid position. I go to greater or equal 0. And now, super extra careful, I forget this half the time, I minus minus. My fingers usually type I plus plus on autopilot, and then I notice when I get an infinite loop. So this way you would go from the back to the front, and like that sometimes happens, why might you want to start at the back? You might simply be tasked with reversing the string. Then it makes sense to start at the back. Sometimes you might be asked to find the last match in a string for whatever reason. And then you'd also want to start at the back. Then you would extract each letter. And this is also something that's worth committing to memory just because it's happening so often. This piece of code gets you the ith character as a string, substring from I to I plus 1. You could also extract it as a character by using the char at function, and then you get it as something of this data type char that we didn't talk about very much. And generally, my advice is don't do it unless you're specifically told to do it. There are a few pitfalls with char. They're numbers, actually. And so sometimes when you print them, they'll print as a number, which is not what you want. So char is only useful. I forgot to finish the sentence here. Something must have happened. If you need to call one of those functions is digit is uppercase, and so on. There are a few predicates in the character class that let you do these kinds of tests. And in that case, char is pretty useful because those tests work on characters and not on strings. In all other cases, you're better off using strings. And that's what we've been practicing in the labs. And the next homework, the one that starts next Monday, has a couple of the ones where you need to use substring.
So I would have to take the car out before doing those tests.
Which one?
Those tests that you just described.
Yes. So for those, you need to extract the character. Now, of course, you could write it if you followed this thing here, and you could still make the test by saying character is digit letter char at 0. That would still work. So basically what I'm saying is try to use this. That way you use strings of length 1. You don't have to learn anything new or extra. Okay, a couple of common errors. Over here we have a very weird looking for loop. Here's one of those for loop artists who tries to cram the entire logic in a for loop. So initialize years with ones. Then he has a years plus plus. But then the condition here, what they do is they update the balance, and then they check whether the result is less than the target balance. Don't code like that. And they cram this all in here, and then in the end they want to print their result. But actually what happens is it's going to print the result n times, not just once. It's going to print 1, 2, 3, 4, 5, 6, 7, and so on, because in all their labor of doing this here, they forgot to put in that naked semicolon. That's not likely a mistake that you're going to make. But here's one that you're overwhelmingly likely going to make one of these days, and in fact, the author of one of the quiz questions made it. And that is to accidentally put a semicolon after the loop. right? Because it's so common. You just type a line of text, and you're used to semicolon, enter. And what this for loop then will do is it will execute its body, which is the naked semicolon, 10 times. It goes from 1 to 10, so it really is 10 times. So it'll do nothing 10 times, and then it'll add sum equals sum plus I. Except in the quiz question, that didn't even work because the I was a local variable of the for loop. The word int was inside the for loop, so it wasn't even defined outside. So this one here is the one that you should be aware. Don't worry about the first one. I shouldn't even have put it on the slide. But this one here is something that happens every once in a while. Same thing with a while loop or with an if, that by accident you put in a semicolon there. Okay, oh, this is an excellent question. How's the network doing? Has it improved? Okay, so now I know how many people are here. Good poll. No. So I is 1. Then it gets incremented by 2. I is 3. And we stay in the loop because 3 is less equal 6. I is 5. We stay in the loop. Then I is 7. 7 is no longer less than equal 6, so we don't stay in the loop. So how many times is the condition evaluated? Let's see. I think. Aha. So I assumes the values 1, 3, 5, and 7. So when I is 1, I is set to 1. Is this condition evaluated, yes or no? Yes, it is evaluated at the very beginning, because sometimes it can happen that at the outset it's not even true. So it is evaluated. Now I is 3. Is the condition evaluated, yes or no? Yes, because it needs to know whether it re-enters the loop. I is set to 5. Is it evaluated? I is 7. And it is one more time evaluated because it needs to figure out whether or not to re-enter. So yes, it is evaluated, and it evaluates to false. Okay, so how many times is it evaluated? 4 times. What was the majority answer? 3 times. So the key here is how many times is the condition evaluated? I did not ask how many times is the loop entered. right? I did not ask how many times as I updated. So with these questions, you have to carefully look at what exactly is being asked for. There was a quiz question just like that where it says, how many values does I assume? And again, notice that I does assume 4 values here. It assumes 1, it assumes 3, it assumes 5, and it assumes 7. The 7 does it no good, but it does assume that value. All right. I guess we're running out of time for this one, so do this on your own initiative. Oh, this is a beautiful question. Yes, maybe I'll come back to it at the beginning of next time. And also, do those 2 loop practices if at all you feel you need some extra practice. You will know whether you need that practice. Have a look at the things, and if you say, oh my God, you need that practice.